Okay, good afternoon, everyone. How's everyone doing? Can you all hear me? Please use the reactions if you can hear me. Great, thanks. Okay, of course, yeah, sorry first of all about the shirt. I see it's the wrong kind of shirt for a Zoom session, so you're getting this interference pattern here. Anyway, we'll switch to shared screen just now. But yeah, the last major set of notes was on isothermal reactor design. And this is where we are starting to touch on actual reactor design. So that's what we'll be covering in this session. Before we jump into it, does anyone have any questions or comments so far? Okay, so there'll be lots of opportunity to speak during the session. So we'll start as we did last time with just reviewing the notes that are there, and then there is an exercise that we'll work through, and it's kind of a semi-tutorial. So I started to write out a detailed solution to all that like last time, but I think it helps if we sort of work through the thing simultaneously instead of me just presenting an already fully developed solution. So let's just first hop over to the notes and see if there are any questions or comments there. Okay, so isothermal reactor design. And so as the preamble says, we are now starting to talk about the actual reactor design, which means what's the volume of the reactor. So moving a bit closer now to our engineering style of things, where we are told there's 50 tons per day that we have to produce, and our reaction rate is on average this value. So what's the volume of reactor that we need to operate at 50 tons per day? So we'll very much be looking at how do you estimate the overall volume for the system. And as we described in the lecture that's on YouTube, an important way to do that is through the Levenspiel plot. I will say that in practice, we don't actually do it through Levenspiel plots. And I'm saying this in terms of some of the longer assignment questions that you'll get, but also in terms of our research in my research group, and also in terms of what I know happens in industry. But it's a useful construct for us just to be able to start to appreciate the sorts of things we have to think about when creating a design. So in developing the Levenspiel plot, we start first with just reminding ourselves what the material balances look like. So all these we developed in the lectures previous to this one. And then we look at the factors that that help us estimate the volume. So our design variable, the volume. So let's look at in the case of the batch reactor how we do that. Well, we know the material balance for the batch reactor looks like this, but there's this derivative in here. So we need to integrate this thing. So if you integrate on both sides, you can show from your basic calculus that the time taken to achieve a specific conversion x is given by this expression. So we are here assuming that we know some kind of production specification. For example, the overall conversion. So we must know what the conversion is that we want finally. Right, so remember, it's a batch reactor. We start out with zero conversion, and we go through all the conversions, and so we pick by picking a final conversion. Then that tells us how long to leave the material reacting in that space. So that's the time needed to accomplish that conversion. And if you follow the integration of your basic material balance, you'll see you basically need to integrate 1 over Ra with respect to x. So here, this is Ra as a function of xa, so that's just to emphasize that, of course, your reaction rate is a function of the conversion. And of course, that's because your conversion influences your concentration. Sorry about that. So your concentration, your conversion, of course, affects your concentration. And if your concentration is affected, then that affects the reaction rate. So definitely reaction rate is varying as conversion varies. So as time is going on in this batch reactor, the conversion is rising, so the concentration is dropping, and hence we are getting a lower reaction rate. So we have to appreciate this is an integral over something that's a variable with respect to this variable xa, and so we have to do this integration. Sorry, I'm just going to try and silence this. Okay, so that's that part, and then of course we also need to know how many moles we put into the space, and so all that together can give us the time taken to accomplish that conversion. And then it's an easy matter then of multiplying by V or dividing by T, and then that tells you that if you want to accomplish this conversion within this time, then that's the size of the reactor that you need. Right, so that's how we can design the batch reactor. And we'll work through this stuff a bit later. Then for the CSTR, our material balance eventually led us to this form. And here, of course, we can replace the space-time by V over Q. And so then you can multiply it out and you can show that the volume is equal to this thing. And so, again, of course, RA is a function of X. So if we do have the final conversion, if we know our production spec, then we just use X here, and then we can use this balance to work out V. And then similarly for the PFR, this is more similar to the batch case, but it has that tau. So if we expand out for tau, and here we just remind ourselves that in the case of the PFR, tau is not one number. In the case of a PFR, remember it's a long tube, and as you look down the tube, you are looking at different volumes. So if you like, you've got the front end of the PFR, and when you are looking at points further away from that front end, you are in effect looking at an increasing volume down the tube. So you can define then your position well, you can define that at some position, the space-time there is the volume up to that point divided by the volumetric flow rate. So there's one volumetric flow rate into that PFR, but the volume we regard as a changing variable down the tube. So the current volume divided by the flow rate, that's space-time. And so we can expand that tau, and then it's dV and Q. And so again, we can repose this. We can strictly write integration of this form, and so that can give us volume as a function of conversion. So again, we can estimate we can find the volume required to accomplish a specific conversion. And you can see again this form, the integral of 1 over RA. And then if we summarize all these, right, for the batch case, we had this one. For the plug flow, we had this form. And you can see in both cases, an integral of 1 over RA. And then for the CSTR, that one's a bit different, but still you can see 1 over RA times XA. So it looks like among all these, if we want the design value V, it's in effect the function 1 over RA that matters, and its dependence on XA. So those two things, minus 1 over RA and its dependence on XA, that decides for us the volume of our reactor. And so that leads us to the Levenspiel plot. So the Levenspiel plot directly shows us that. It's a plot of 1 over RA against XA. And so when we look at this plot, we can then think about how those three cases appear in terms of the volume. Any questions or comments there so far? I guess not. Okay. Yeah, just please remember to unmute yourself if you have a question. Yeah, so unmute yourself and then you'll be able to ask the question. So that's your Levenspiel plot, and then let's see now what we can do with that plot. So here I'm just repeating what we already said, right? The same volume equals the Levenspiel type things. And so if you think about, let's think about the batch case. So we are interested in this integral. And if you think of it, of course, if we were to write an integral, right, so if you wanted to know what's the integral f equals integral of f of x in x, and let's say we wanted it between between x naught. Let's move you in here. Ugh. Well, that's not going to work. Yeah, okay. Well, so if we want to know the integral like this, where there's some function f of x, and we are integrating between some value x naught and some other value xn, then of course, intuitively or geometrically, we think of this simply as the area under the curve f of x, right? Now, if you look at the form we have here, our function is 1 over Ra. So this is nothing but the area under the curve 1 over Ra. And in our Levenspiel plot, we are plotting 1 over Ra. So we've got our curve 1 over Ra. And so in this case, in the batch case, it's simply the area underneath that. So that area, that's your batch case there. And similarly for your PFR, it's the area under that curve. For your Cstr, on the other hand, it's more like xa times 1 over Ra. And so it's xa, remember this axis is xa, and then 1 over Ra is this value. So if you take the product of 1 over Ra, which is this height, and xa, which is this length, then the product of those two is that area 1 plus area 2, whereas the batch and plug flow cases are only proportional to area 2, the integral under the curve. So you see in the Cstr case, you've got this extra area 1, which means that there's going to be additional volume required. And we had said before that's because the Cstr is the worst user of its reaction volume. And that's because the Cstr is perfectly mixed everywhere. So in all space, it's the same. And then also when we say Cstr, normally we mean steady state. So it's the same both in time and space. That means if you have a high reaction rate or a high conversion, then you have the same low concentration everywhere in that Cstr. So we said all this, right? We've been saying it for some time now, and now in this session we want to look at, can we design around that? Is there a way for us still to get a decent reaction rate and hence reduce this problem of this extra volume? Is there a way to reduce that extra volume? And so yeah, we'll be looking at strategies for that. And the reason we are interested in that, it's because this is the clearest one for us to construct. We just we know how to make this in the engineering sense. For plug flow, we don't really know how to do that. Fluids don't really behave like plug flow, so engineering-wise, this is hard to do. This is fairly easy to do, but we know there's lots of interrupted action here. So anyway, that's there. Please let me know if there are any questions or comments there. So there is this example here. I won't go through it now. Please work through this example. I guess regard it as your first tutorial question, if you like. And then we can think about the case when the Levenspiel plot looks like this. So in the earlier case, it was for a fairly straightforward case where you have a first order reaction. So if R equals kCa, which is very often in reaction engineering, you'll meet R equals kCa. First order reactions are often used. So if R equals kCa, then you get this typical kind of curve. And in this case, the Cstr is the clear loser because you've got this extra required volume. However, if you have some other weird reaction kinetics, so let's say you had kinetics like this, where your rate is actually inversely proportional to your concentration of the reactant. So as your reactant concentration goes up, your rate goes down. And this can happen in certain systems. So you have certain catalysts where if you have too much reactant, then the reactant actually starts blocking the active sites of the catalyst, and so that reduces the reaction rate. Another example is in the biosciences, where you have little bugs, where you have bacterial. Okay, thank you. So if you have bacterial activity that's promoting your reactor, your reaction, then if you have too high a concentration of the substrate, so the matter that the biomass consumes, if you have too much substrate, then that in effect poisons the biomass, and so that reduces the reaction rate. So this does happen. It's not as common as the other case where the more reactant you have, the higher the reaction rate. So that's the most common case, but this can happen. So in a case like this, your curve might look something like this. So in contrast to the other case where the curve slopes up, in this case, it's an inverse relationship. And in this case, your Cstr is actually doing better than your Pfr and your batch reactor. So the area under the curve in this case is greater than the product at that point. Right, so that's one. And then quite often our kinetics are rather complicated, and you get strange bumps and things in your reaction rate as a function of conversion. So it might easily happen that you'll get 1 over Ra doing something like this. And so in this case, again, there isn't a completely clear answer. So if you think of it, the best arrangement in this case would be to use a Cstr here. So if you pick that Cstr, then you are saving all this volume. And then with your Pfr here, yeah, thank you. Yeah. Close the door, please.
Yeah, I want to tell us something.
I'm in a class now.
Okay.
Okay, thank you.
And Dad, can we also get an Xbox One?
Yeah. Okay. Okay. Sorry about that. Yeah. When you're on Zoom, you can't yell at your kids the way you normally would. So you have to be. Yeah. So there's you can't get the normal discipline levels there. But anyway. So yeah, if you've got your Pfr, you'll say that beyond this point, the area under the curve is going to be less than the product. So if you imagine taking a point here, the product then would have all this wasted space. So on this side of it, your integral type reactors are better. So yeah, we can call them integral type reactors. So Pfr and, well, actually integral means something else as well. But anyway, the Pfr and batch do perform better in this region. But if you tried to use them here, let's say you used a Pfr in this case, then you see you have all this extra space for the Pfr here. So by using a combination of reactor types, you can achieve the kind of you can achieve a better volume reduction. So if you like, this is the first hint that our approach to design is not such a straightforward thing. So the kinetics can actually dictate what we do in the real world, in our engineering world. We have to try and navigate nature. So if you like, nature has decided that this is the curve, that as you convert component A, your reaction rate changes in some way, and so this quantity looks like this. So that's all nature. And now we as reactor designers have to cleverly navigate this plane of kinetics so that we have the features that we want, namely a low capital cost at this stage. There are other costs that we'll consider later, but to get a nice low capital cost, we can see that it's best to use a Cstr with a Pfr. Any questions or comments there? Okay, then I mentioned here the Darmkühler number. Yeah, you can read about that. And so if we think about it, let's go back to the most standard type of problem where you've got a monotonic increase in 1 over Ra. So you've got this kind of behavior. And if we wanted to accomplish some specific conversion, let's say x3, if you use just one CSTR, clearly you are going to waste all this volume here. If you use a series of CSTRs, we can see that we are saving quite a lot of that volume. So that's what CSTRs in series give us. And then we can think about strategies towards that. So we can think about having the same conversion in each CSTR. We can think about keeping the volumes the same, or we can think about minimizing the total volume. So these are all strategies that are described in detail in that video. And if you have infinite CSTRs in series, you can show mathematically that you are getting closer and closer to a plug flow type behavior. And so, as we said in the video, as you vary n, as you increase n, you are getting closer and closer to plug flow behavior. However, you can limit your value of n. So it's not the case that n has to be 1 or infinity. You are free to choose, as the reactor designer, you are free to choose an intermediate value for n. So if you choose 2 or 3, you can see already you are getting volume improvements. So you are basically getting this in-between state. So it's in between where you have to have perfect mixing and no change in time, and where you have perfect not mixing. So you can balance between those extrema. Okay, and then there are some other cases here. So this just makes your material balance more interesting in a way. More practically, in this case, you could maintain a high concentration in this batch reactor. So the batch reactor, as we said, loses concentration with time, and so in this way, at least you could maintain your high concentration and so maintain a high reaction rate. Here, it might be that the presence of the product actually retards the reaction, or it might be causing pressure problems. So you could withdraw your product over time. And then, for pressure drop, we had talked about the volume expansion term in the case of gas flow reactors. So in the gas case, you should also account for pressure drop. And you've seen in detail in the fluid mechanics course how to estimate that. And so you can correct for pressure drop here, and so you can get a better estimate of the concentration, and so get a more accurate value for your reaction rate. That was basically what was in the lecture there. So that's just a recap. So what we want to do today is work through an exercise where we apply this, and so we'll take each of these types of problems and estimate the volume. So let's just start looking, I guess, here. So let's take an example here. Where are you? Here. So in this exercise, we are given our reaction stoichiometry. So you've got a component A, which is being converted to two molecules of component B, and we are given a rate expression. And I'm not really going to stick to this rate expression. I want to show some features of this. But here's a rate expression, and we may play around with a couple of different rate expressions. And we want to know, number one, it's always useful to do this exercise where you consider how concentration will change in the batch reactor. And remember, your batch reactor looks like this. So in terms of its balance, it looks like this. So I always like to start with a batch reactor, and because your concentration and your reaction rate are so closely related, so there isn't an influence from flow or the volume and things like that. So it's always nice to start with a batch reactor and get a sense for how the kinetics work in that case. So let's first just simulate that batch reactor, and to do that, of course, we take out our trusty Python, and so here I've put in some specs for the problem, and here's the rate expression. So I'm specifying a certain conversion, and I'm specifying a reference concentration for component A. So remember, the reference concentration, that's either the inlet concentration or the initial concentration. So both those are related to how much you have kind of before reaction happens. So it's a generalization of that concept. So we just say reference concentration. By that we can understand it as initial or inlet concentration. So always your current concentration is your reference concentration times 1 minus the conversion of that component. Then in this case, A is converted to form 2B, so CB is twice that, right? So that's concentration of A and B, and then we can put our reaction expression here. So like I mentioned, we'll play around with a couple of different rate expressions, but for right now, we can stick with the one that's given in that write-up there. So this function is going to give us the reaction rate if we supply the reference concentration and the current conversion. Okay, and we can just run that and run, and here all I'm doing is plotting the Levenspiel plot. Well, that's not all I'm doing, but we'll come to that. So here we are just plotting the reaction rate itself. So let's plot that. And you see this it looks like something weird is going on here. So you're getting a reaction rate that looks close to 0, and then it shoots up, and it looks like it might be going off to infinity. So if you increase the resolution here, you'll find that number goes up further and further. So anyway, let's put this back. So we can see it's shooting off to infinity here, and then it's coming back down to 0. So it looks like there's a special value over here. And if you think about it, if you look at this expression, you can see that depending on the value of K2, there will be a value of CB where your denominator is going closer to 0. So you are taking a finite fixed number and dividing by a number close to 0 at some point. And so the reaction rate will spike around there. So we do expect to see this. So we expect that the rate will spike somewhere, and otherwise it's giving us finite numbers. So that's what our rate expression looks like. So it's always useful to understand how your rate is changing as conversion changes. And what we really want is the Levenspiel plot, right? So yeah, in fact, we can't. We get this curve here. We might not really expect this nice looking curve because it looks like we should see some spike somewhere and it should be flat and so on. And that's just because the spike is dominating things. We can't see easily that there is some variation here. So maybe if I just drop this resolution, we can see something. So you can see there is curvature in these regions also, and so you get some. You can see the curvature here, and it's just the case that when you do 1 over RA, it's a bit easier, because 1 over RA, this goes in the numerator, and then you can see the denominator is not getting close to 0 anywhere. So just the numerator gets close to 0. So when you plot 1 over RA, it's just the case that the number goes close to 0 there, which is not a problem in this case. So that's the curve, that's the Levenspiel plot for that rate expression. Okay, now we wanted to look at the batch response. So for the batch case, dc dt is RA. So we can first we can estimate the rate the reaction rate, and actually here I've defined a little function. Well, we talked about this, I think. Yeah, we said this just now, that we've defined a function here that gives us the reaction rate if we supply the reference concentration and the conversion. So we have this function. So here we are just simply using that function. So we are estimating the rate of formation, and we know from our material balance that for the batch case, dx dt is minus RA divided by the reference concentration. So this is straightforward. This is the material balance. So this then defines for us the differential equation for the batch reactor, and then we can use ODE int to integrate that with time. And if you run that, it's pretty boring actually. Your conversion is just rising with time. We could think about increasing the range there. Let's go for 2 space times instead. Okay, 20 even. But yeah, it seems to saturate. I'm not convinced that's right there. So times 2 is getting to the right thing here. Well, that's conversion. So so it might well be. Let's see. Well, if your conversion, if your rate is extremely close to 0 here, then granting more time for reaction will not result in further reaction. So it looks like here, when you formed enough product, right? If Cb concentration is high enough, then your denominator is quite high. That means your reaction rate is very close to 0. So if that's the case, if your rate is very low, then it doesn't help to give more time in that batch reactor, and so your conversion doesn't rise much more after that. So so that's one. And then going further here, we want to estimate, in fact, let's estimate the volume for the batch case. Right, so if we want to know the volume for the batch reactor, then we go back here. We can see this is our batch balance. So here, estimate batch volume. So that's the expression we want. And we can see here we need to find this integral first. So we know RA is some function in XA, and we need to find that integral. And let's talk about numerically how we can estimate this. So we want int sub-0, so int sub-0 super XA. Now you can let's see, this is going to be a problem. Sub-zero. Super X. Yeah. Okay, anyway, that's the integral we want, and then the way to estimate that is through a Riemann approximation. So if you are looking for the integral of f of x, then you could estimate that just by taking, and let's just sketch what that means first. So let's say you've got some function f of x, and you wanted to know the integral between 2 points. So according to your Riemann approximation, you would break this space up. You would break this curve up into discrete elements, and you would estimate the area of each of these discrete elements, and in that way, then you would add them all up, and that would be an estimate of the area under the curve. So to do that, let's say it's this panel we wanted to estimate. Right, so you could say my estimate of the area here is simply the difference between these two values. So let's say this is x and this is y. Then, yeah, I don't know if I can write too easily here. So clearly there's a delta x, so let's just say dx. So there's a dx equals x I plus 1 minus xi. So I'm just going to write it here. So delta x equals x sub I plus 1 minus x sub I. Right, so that delta x is basically that distance. And then we need a number, we need to know the height here. And of course the height is changing as you move along this curve, right? Especially over here, you can see that if your panel was here, then your height is a variable thing. But there does exist some average height here, right? So if you have if your panel is actually here, where's the brush? So if your height is if your panel is here, then this is the area that you want, and an approximation to this area is to take the average height in this space. So your average height here, right, multiplied with that width is an estimate of the area. So we can define for ourselves the average height. So you can say here y sub I bar equals, and 1/2. So it's just we could just talk about a linear average in this case. So yi plus yi plus 1. Right. So that's an estimate of the average value of y, and so your Riemann integral is nothing but the sum of all those, sum I, and then it's going to be your mean value of y in each case, multiplied with your delta x. This should be delta x I. So that's so when you hear about Riemann integration and you hear about trapezoidal rule and so on, don't just memorize formulae. Just make a quick sketch like this, and it's all quite obvious. It's this distance divided by the average height here, which is the average of these two heights, right? That's all it is. So that's your Riemann approximation. And so what I'm doing here is actually estimating that Riemann area in the same way. So here I'm estimating delta XA, and here I'm estimating the average 1 over RA value. So I'm doing this at each interval. And I think I didn't even say that I'm generating a set of values for XA. So if you look here, we've chosen a linearly spaced set of points. Right, so in XA, we know the smallest possible value is 0 and the highest possible value is 1. So we are free to choose any grid space. So here I'm choosing 200 points between 0 and 1, and you can increase that or decrease that as you like. So anyway, for 200 points, it's giving us a fairly smooth curve, and we are estimating then at each interval of that 1 over 200, each interval being about 1 over 200, we can work out a delta x there, and then for each tiny interval, we can also work out an average height there. So that's that average height. And here I'm creating a vector of all these little areas. So like we said here, at each panel there exists their own area. And so I'm just putting all those little areas together in one vector, which I call di. And then I'm looking for the cumulative sum of di. So in this case, it's basically this operation. We can say f of x is the cumulative integral, so f of x in dx. Right, let me try something here in terms of getting those limits. Yeah, that didn't work. All right, anyway, so we are taking the cumulative integral. That means we work out the contribution from each of these little pieces. So we add them up progressively, and then that gives us, so that's what I'm doing here. I'm working out I, which is the cumulative integral of all these pieces. And so that's giving me the integral under 1 over RA. So that's shown here. And if you compare these two, you can see here 1 over RA is a positive number, but it's decreasing towards 0. So as you move along here, and these are negative numbers. So as you move along here, this number is increasing, or if you say it's negative, then that's decreasing. Then you get to a place where it's close to 0 all the time. So down here, there isn't further contribution to the integral. It's all 0, so you're just adding 0 in this region. So you can see it's flattened out here. And then as you go further here, you can see you are getting these numbers again. So you are gaining to your integral again. So your integral is getting bigger and bigger out here, but it's negative, so it shows up as it going down further. So here it went down to some extent. Then there was a period where there was not much further contribution to the integral, and then it started dropping again. So this curve is very much the integral of this one. And we got it just by doing numerical integration. We didn't use any function or anything like that here. Okay, so we have reaction rate as a function of conversion. We have the Levenspiel plot here, and we have the integral of the Levenspiel plot as well. And here you can see we've got some nice weird kinetics, right? You can see here that you've got a portion where the Cstr actually performs better. So if you pick a value here, you'll get a nice small Cstr. And then as you go past that point, you can see the reactors with integral terms will perform better. So that's a nice set of kinetics to work with. Okay, so what did we want to do? We wanted to estimate the batch volume, which we said was this. So let's say let's define a bit of a question for ourselves, and let's say, just put that away. So let's say, what's the volume to achieve, let's say, 80% conversion after 2 hours of operation? Right, so let's say that's the specification. Then clearly we need to integrate 0 to 80% here. And so we can just look then at this curve. So we have this nice integral available to us already. So we could simply say, well, 80% is here, so my number here is about minus 0.113. Right, so the integral part is minus 0.13. So that totally takes care of this part here. And then Na naught, so that's the amount that we have charged into the reactor. We do need to specify that. So what's the volume to achieve 80% conversion of, let's say, 20,000 moles? So 2 times 10 to the 3 moles of A after 2 hours of operation. So it's going to be 20,000 moles, 20E3 times minus 0.13 divided by 2 hours of operation. Right, so, and that's all we have to do in that case. So that then gives us a volume. That's the batch volume we require to accomplish this. Yeah, you won't be able to do this in a test or an exam, right? So if it's a test or an exam, what you would more likely do is break this integral up into a couple of pieces. So we could say here the integral for, and I'm just going to call it f of x. We can break that up into the integral, and let's use this notation, integral. So integral, and here let's say, so let's say here we are going from so let's say we are going from 0 to 0.8. So we would like to integrate from 0 to 0.8. And what we are going to do is break up this integral into some pieces. So we'll say 0 to 0. Let's just do 2 panels, 0 to 0.4 plus 0.4 to 0.8. Right, so our limits, overall, we want to know this integral from 0 to 0.8, and we can get the same result if we break this integration up from 0 to 0.4 and then 0.4 to 0.8. And so if you look at your curve, you can say, well, 0 to 0.4, just by looking at this, I can estimate a kind of triangle here. So it's 0.4 multiplied by 0.4 divided by 2. So we can say here, this is approximately 0.4 times 0.4 over 2. Plus, and on this side, you've got 0.8 and 0.4, so this triangle It's yeah, the average value here, let's just take that as 0.4 as well. So in fact, it looks like two similar sized triangles here. And so here you've got 0.4 also times 0.4 over 2. Right, so that's an estimate of that part, and then you multiply by the other numbers, and that estimates the volume for you. Don't waste too much time on integrating this accurately, because clearly you can always write code and do it very accurately. You can do it to nth decimal place. So it's pointless in a test or an exam trying to get a very accurate number for this. So you'd rather break up the integral, show that you have a good appreciation of how to quickly and easily estimate an integral, and that's all you need to do. So don't make these terms stress you out, and don't try to do too much with it. In this course, nobody's testing your performance level in numerically estimating things, right? So that's a quick way to estimate your area here, and then the rest is just algebra. Any questions or comments so far? Right, so that's what you can do for the batch case. For the CSTR, it's quite straightforward. For the CSTR, you've got this balance. So we simply take the conversion 0.8, and now you have to look up the reaction rate at that point. Right, so here let's apply the same numbers. So we are going to say it's so many moles, and so let's say FA in is defined. So I'm just going to write it FA in. So let's say that's defined. Then we want a conversion of 0.8, so that's defined. That's fairly clear. And then the other thing we need is the reaction rate. So here, for 0.8, here's 1 over RA, so it's about 0.65. So times 0.65, and in fact I think that's negative. So I've been or I read here from the Levenspiel plot, so that's already 1 over RA, so that's why it's times, right? You could read this as XA times 1 over RA. So 1 over RA is minus 0.65, and then times 0.8. That's the volume that we need. So that's how we can estimate the required volume to accomplish that conversion given a specific molar flow rate. That's the CSTR, and then of course for the PFR we have a very similar thing to the batch case. So for the PFR, you already have this integral. You've estimated it here. And then in this case, it's the molar flow rate. So the molar flow rate times that integral is going to give us the volume, the required volume for that PFR. Okay, so that's how you estimate the volumes in this case. Any questions or comments there? Okay, now moving on, let's look at some of these other cases. So we do have a curve like this. So let's consider CSTR and PFR. Now, in fact, in this case, it's a bit extreme. You are not going to get good numbers here because this value is so close to 0. So we are going to end up saying that it's a 0 size CSTR here, which doesn't make any sense. There's your CSTR. So typically this would be some finite number. and then you would add up. So we've already talked about how to estimate that area and hence the volume there. And then for the CSTR, we've shown how you just look up the RA value. In this case, it's 0. It doesn't make sense. You will end up with a 0 volume CSTR. But anyway, for more realistic kinetics, you'll get some finite value. So it will be that number multiplied with that conversion, so 0.4. So I'm just going to change things a bit here and say, so CSTR plus PFR, and let's just say imagine the minimum value equals 0.1, right? So then the volume in this case, V CSTR plus PFR equals, so the volume of the CSTR part is going to be FA in times XA over RA, so times XA over RA, and then plus, and here, so let's say the minimum value is 0.1 at XA equals 0.4, right? So it's going to be this plus this integral, the integral going from let's call it x1 so x1 to x2, and this is of also it's dxa over ra minus ra, right? Okay, so CSTR plus PFR for these choices here. So and there's an FA in over here. So I'm just going to take this FA in out here, right? It's basically like a constant here. So XA over RA, XA here is 0.1. So 0.1 divided by RA, which we've said is 0.1 also. So sorry, this is 0.4. So the CSTR part is 0.4, and RA, or 1 over RA, is 0.1. So I should say here 0.4 times 0.1, 0.4 times 0.1. So that's the CSTR contribution, plus, and then your PFR contribution here, so it's between 0.4 and 0.8. If you look here, you can see the average value of 1 over RA, let's take that as 0.3. So to estimate this, we are just going to say it's 0.8 minus 0.4 times, and it looks like 0.3 there. Right, so this is an estimate of the volume of the CSTR plus the PFR parts. Now, if we compare that with the reverse, so if we did the PFR first, right, then we have to swap these around. And in fact, here I should have written this as an x1, right? So now we are going to write the PFR part first, and so this one is now going to go from 0 to x1, and then here the CSTR part is not going to be x1 anymore. This is going to be x2 minus x1. And in fact, we should also be more careful here. So clearly this this rate is between 0 and x1. This one we have to, what do we have to do? We have to choose the end value. This CSTR is all going to have a conversion of x2. So this we can call RA2. So we should have said here RA1 also. So once again, let's just look at what we did in the first case. We took this ratio. We said that we assumed this value was 0.1 here. And so that's referring to 1 over RA 0.1. And you see there, I'm taking the value here at this point, at this x value. And you might say, well, why didn't you take the value here instead? Right? That's because when you look at the CSTR is operating at its exit concentration. Right? Think of a CSTR. It's perfectly mixed there, and so the concentration in the CSTR is the same as the concentration at the exit point. It's not the same as the concentration at the inlet point. So your content of your CSTR is the concentration at the exit point. So at the exit point, you use the exit conditions here. So the reaction rate that we used here was 1 over RA is 0.1. We didn't use 1 over RA as being that inlet value. So this is the part to be careful of. I know it looks all very easy to approximate, but this is where we check. We have to get these numbers right. Okay, so you see that's going to be different now in this case. So in this case where the CSTR comes second, right, then the CSTR is going to operate at the 0.8 value. So at 0.8, here's your 1 over RA, so the value here is 0.6. So for the CSTR, this is a 0.6 here. Okay, and then we need to estimate for the PFR part. So this is the PFR part. So this is the area from 0 to 0.4. So it's the area of this triangle here. And you can say that the average height here is about 0.18, and that's 0.4. So 0.4 times 0.18. And if you look at this, you can see the numbers. You've got the same 0.4. So I'm comparing these two configurations where you've got the CSTR first compared with the PFR, and here, right, and the reverse here. So here the first term is going to be bigger. You've got the same 0.4 here, but the second factor is 0.18 in this case. And similarly here, you've got the same 0.8 minus 0.4, but your factor here is twice the value as there. So your PFR plus CSTR is definitely going to be bigger than in the first case. So it does matter what order you have these in, which is a surprising result, right? We might think, well, I've got a PFR and I've got a CSTR. What does it matter what order I put those two in? And we can see here it does matter, at least in terms of these numbers. We can see it does matter. And then if we think about it a bit further, it matters because in terms of these weird kinetics, we are able to get a low, we are able to get basically a high reaction rate for our CSTR, right? You're having a high conversion under these weird kinetics. A high conversion actually means a better rate. So you'd in your CSTR, we know the CSTR is always going to give us a low concentration. And so if you have a low concentration in a region where a low concentration means a high reaction rate, then you've navigated the kinetics successfully, right? So once more, your CSTR always works at a lower concentration, and you've got kinetics in this case where a low concentration gives you a high reaction rate. So by putting the CSTR first, we've taken advantage of these kinetics and we've achieved a high reaction rate in that CSTR. By putting the CSTR second, we are now in a region where a high conversion translates to a low reaction rate. So when you put it second, your reaction rate in the CSTR, even though it's the same CSTR, your reaction rate is lower there. And you could make similar arguments about the PFR. So it's not just a mechanical thing. The order matters, and it's not just mathematical. It also, in terms of kinetics and navigating the plane of kinetics, we can see it makes a difference there. Any questions or comments there? Okay, and then in terms of the other questions, yeah, the minimum volume. So, have a look at what we said here. If you are looking at a CSTR, at two CSTRs, can you estimate the best possible choice for x1? So here's your curve. In this case, our case is a bit different. So you've got some Levenspiel curve, and you know what final conversion you want to accomplish, and you are free to choose the intermediate conversion. So you can pick any conversion for the first CSTR, and that then defines each volume. And we want to make a good choice for x1 such that we get the smallest total volume. And from the developments, and we discussed it in, I guess, enough detail in the notes. From that discussion, we find that the way to do it is, number one, we estimate the gradient at this point. So if you choose x1, that then prescribes a specific point on this curve. So once we know that point, then we can estimate a specific gradient to that point, right? So you can see here, that's the gradient at that point. And then when you choose this point, that also specifies this point, right? Because we've defined our x2, so that specifies this point. So we've got this point and this point specified. So that point then becomes specified. And then moving horizontally here, that also specifies that point. So we can draw a line here. So that defines this line, and then you've got a gradient here, and you've got another gradient here. And so you want to shift this x value, you want to shift x1 around until this gradient equals this gradient. So there will exist a specific x1 value where those two gradients are equal. And if you read this proof carefully, this explains why equality of those gradients translates to the minimum reactor volume. Right, so you can do that on this curve. But in regions here, maybe you would actually just do it between 0.4 and 0.8. So if you have two CSTRs between 0.4 and 0.8, we know that's not a good choice for these kinetics, but let's say we did it anyway. Then what's the intermediate value between those two CSTRs, which give us the minimum volume? So again, you can look up the gradient of this line here, and then you can look up the empty space volume, and hence that line. And where the gradients are equal, then that's the minimum volume. Okay, so that's pretty much all I wanted to do today. Are there any other topics that you want to cover? How do I do this? Okay, so I guess I'm not really hearing anything. So if there are any topics, is there anything in the chat here? Okay, so a couple of questions here. Does the PFR have the same volume as the batch if the molar flow is equal to the average? Yeah, so let's go back here. Sorry, I didn't answer this question when you asked it at the time. How do I minimize this? So you've got these two equations. Okay, let's look at it here. Not there. Here. So the question is, if you could get these two numbers to be equivalent, right? Let's start with the batch case. So let's say we specified a molar inlet flow rate. Then you could say, in the case of the batch reactor, you could identify an equivalent inlet molar flow rate, right? In the batch case, we don't have flow, but we put a certain number of moles into the reactor in the first place, and then we run that batch reactor for a specific period of time. So let's say you put 1,000 moles into that reactor, and then you ran that reactor for 2 hours. So 1,000 moles in, and you've run it for 2 hours. Then you could say, well, that's equivalent to having 500 moles per hour, right? So you just divide the total number of moles you put in by the total time you ran that reactor for. So 500 moles per hour. And so you could have equivalently created a plug flow reactor and fed it at 500 moles per hour. So yes, you can find equivalence between flow rate and charging amount. And then these two are identical, right? If you are converting both those to the same extent, right, to the same x value, then everything is identical, and these two volumes are the same. So that's true. You can get the, if you are trying to keep the average molar flow rate the same, you'll get the exact same volume in the batch and the plug flow cases. Another way to look at it is that the batch reactor, it's basically looking at snapshots in time. So let's say you look at the batch reactor at time 0. So it looks a certain way. There's a certain concentration in that batch reactor. Then you look at that reactor 1 hour later. Then it looks a certain other way. So you are looking at that batch reactor as it's changing in time. Now, if you look at the plug flow reactor instead, if you look at position 1, right? So you've got your tube, and at the inlet point, right, where Z equals 0 or V equals 0, you've got a certain concentration there. You'll have the same concentration as the equivalent batch reactor at time 0. So time equals 0 is equivalent to Z equals 0 in the PFR case. And then if you look at the PFR halfway down its length, that will be equivalent to the batch reactor at half its duration of operation. So time and space are interchangeable. So you can think of the PFR as distributing you across space, and the batch as distributing you across time. And you can easily translate between the two, right, simply through the velocity. So if your fluid is flowing at velocity u, right, u equals z over t, so you can easily translate between z and t through u. So yes, the batch and plug flow cases are equivalent. You can get the same volume if you've taken the trouble to keep the equivalent molar flow rates equal. Where are the rest of those comments? So just bear with me here. Sorry, I'm really having trouble. The participants and okay, so the PFR, right? Does that answer that question? And then will we be given all the graphs in a test? So it depends what's being tested If you are being tested about your ability to draw that graph, then of course you won't be given that graph. To questions like this, I typically say you'll be tested in a certain way, and you'll be given the credit according to what's being tested. So if you are being tested on drawing the graph, then you won't be given the graph, but you'll be given marks for drawing the graph. If you are required to design the reactor and you are not given the graph, then there'll be more marks in that question for drawing the graph and for working out the design. That's as much as I can say until I actually set a test and so on. Okay, are there any other questions or comments then? Okay, if not, I guess that's it. Thank you all for listening, and I'll be releasing further notes. We'll be moving on to the next section, the energy balance. There will be more questions for you to practice the isothermal reactor design on. So, and I may release further notes on that sort of extension of tutorial. So there will be more material on the isothermal reactor design part, but in terms of the lectures, we'll be moving on to the energy balance, and you'll get a video on that later in the week. Okay, that's it for today. Thanks everyone.